CloudDB, shaping your new normal.
Hi everyone, welcome to the APAC OUC event. Full disclosure, I've pre-recorded this session mainly because in Perth I was having a bit of drama with the latency between this and the event platform, and I didn't want to give you a choppy, granular, hard to understand video. So this is pre-recorded, but I'm sitting here live in the chat, so if you have any questions, throw them in the chat and I'll answer them. Anyway, on with the presentation. Welcome everybody, my name's Connor Mcdonald. I'm a database advocate for Oracle Corporation. Now the title, From Bitbucket to Extreme Performance. What exactly do I mean by that? It means this: as IT professionals, we always have ideas. We'll be doing something mundane like walking our dog, and all of a sudden an idea springs into our mind. Something that's going to be a fantastic application, something that's going to take the world by storm. The problem with these ideas is you have an idea in January, and often the time it takes to get that idea into something, into fruition, into a real solution, is a huge amount of time, and all of that represents lost opportunity. Ideally, we want to take our idea from the moment we have it and literally, in the case of maybe minutes or hours, have a website up and running. It might not be the fully fledged product, but at least we have the ability to start getting people interested. We're starting to sow the seeds of this idea into the world. So we want people to be able to join up, register their interest, etc. We want to get that idea up and running as soon as we can. The problem is the number of lines of code we have so far is 0. And that's a problem. That's going to obviously take time. What we really need is just some mechanism of storing data. As long as we can get people interested, have them register, we just need some persistence. We don't need too much rigor at the moment. And the perfect model for that is JSON. Very flexible, very easy to take from, say, a JavaScript application, grab some JSON and just store it in the database. And to store it, literally, it's just a few lines of code if you're using something like Soda. So very, very quick from idea to a website. And if you want, obviously, you don't even need to do any hardware. You simply grab one of our cloud services and you're off and running with, say, autonomous JSON. Now the time frame from idea to website is almost 0. And the great thing is, as your idea evolves and you start getting more ideas, you might want to change your website. You might want to take some surveys of customers, or they even might want to participate in, say, a beta. This rapid style evolution is also very easy with something like JSON because the JSON is very flexible. You can simply evolve it over time, store whatever you want as your application sort of goes from Genesis into something that's going to be a little bit more realistic. And the cool thing is, even though it's JSON, as you start collecting this information, if you want to start doing trend analysis of it or start looking at stuff in a more relational fashion, it's easy with some of the JSON features available. So you can simply dump JSON and still get some sort of relational facilities out of it. Eventually, though, you want to actually start taking people's money. And that's perhaps a bit of a time where you might want to step back and think, well, this application has gone from idea to something that's real. It's a financial thing. It's a commercial activity. Now's the time we might want to actually look at adding a bit of rigor. The problem is the jump from just storing any information that comes from my website into a relational database structure with rigor and all the great properties of relational databases, it's a big jump. All of a sudden, I've got all this DDL, etc. to write. I've got a lot of properties to understand. That's a big jump from just storing JSON. The great mechanism we have for doing that, to make that jump easier, is a thing called QuickSQL. You can go to quicksql.oracle.com. You notice you actually can create a relational database structure in the same way that you would actually store your JSON. It's just a nice hierarchy there. I'm going to have some customers with some various details. Those customers are going to have some orders, and each order will have some items, and those items will consist of various products and quantities. I pretty much just lay it out almost in the structure I have with my JSON. And QuickSQL does the heavy lifting of generating all the DDL required to build that relational structure. That's going to be our starting model here. I've finally taken my application, I've added a little bit of rigor, I've used QuickSQL to build a convincing data model. So this is what QuickSQL built me. It gave me a customers table with some attributes. It gave me a product categories table. It gave me some products. It gave me an orders table. And you can see the primary keys and indexes are all being built for me. It gave me an order items table. It put all the foreign keys on. All this stuff came out of QuickSQL for me. This is your first logical jump when building applications and moving from, say, JSON to a relational structure. Don't get me wrong. That is a great model. I'm not saying this is something that you would just start with. This is a really good model, and you can do industrial strength applications with this. That's fantastic. What if, though, your idea was one of those great ideas that actually became a worldwide hit? You've suddenly gone from a commercial application to something which is now an absolute global blockbuster. You can hit what we call a success crisis. A success crisis is when your application is literally so incredibly successful that you might now need to take that next step in terms of relational theory. And this is one of those sad moments where people have these things called success crises, and rather than stepping back and looking at their relational model, they race out and they start writing blog posts saying, oh yes, we hit the limits of relational theory, we have to move to some other platform, we have to introduce huge amounts of complexity because relational doesn't scale. That is just complete fiction. Let's do a demo now with our starting model and see how good the database is just with what came out of QuickSQL. So just to show you, we're going to quickly run through the script that QuickSQL came out. It created us a customers table. It created us some products and put the various constraints on. We had an orders table, some order items, etc. This is what came out of QuickSQL. And you can see that QuickSQL has also enabled some basic auditing facilities for me. On each of the tables that are about to be created, it has added a created by column to track who created the row. QuickSQL also typically adds a created time as well. You'll see shortly that QuickSQL creates a trigger to capture those values in those columns. It also gave us our foreign keys, which is nice. It also handles things like surrogate keys, population of surrogate keys, all the things that you would normally have to handcraft, it takes care of for you. It created the sequences, gave me some triggers to populate surrogate keys if they're left out, and the created by column is populated as well. One on customers, one on orders, one on order items. I'll put in some sample data there just to seed the tables to get going, because I need some customers and products at least initially so that I can start taking orders against them. And here's our application. The ability to create a new order, create a new customer, add some order items, just written with some simple PL/SQL procedures. And what I'm going to do is create a little benchmark application here, which will let me stress test this data model. I've got a little table here called results, which will serve two purposes. When I run my benchmark with multiple concurrent sessions, each one of them will record their elapsed time and transactions per second in the results table. But also, at the start of each benchmark, they will attempt to get a lock on this table or a row in this table so that I can control exactly when the concurrent sessions will all start. And here's a little benchmark utility I've written just in PL/SQL. You can see two routines at the bottom of the code called init and run. Init will build up a list of random customer and product IDs to create orders. We use dbms random and the seed procedure to ensure that each benchmark will use the exact same set of random data to ensure consistency of results. We're going to place 40,000 orders, and every 200 orders we're going to create a brand new customer. We're simulating lots of activity. This benchmark will actually run in concurrent sessions. There's the rest of our benchmark, and when it's finished, we update our results table to actually store some metrics that we can then look at. So what I'm going to do now is lock my results table, and this will stop all my benchmark programs dead in their tracks before they start to make sure they all start together. I've launched off another 6 SQL Plus sessions here, all of which are now about to start our benchmark, which is going to slam away orders and customers as fast as it can. They won't start until I hit commit. Let's give that a go. Now this benchmark has now got 6 concurrent sessions, all literally as hard as they can, slamming away at this relational model to see how many orders per second I can place. Let's see how we go. And once the benchmark is finished, it will actually give us a summary of what those 6 little children did in terms of working their way through. And here's our summary. You'll see the other little slaves fall away and disappear shortly. So what did we get? On average, a slave took about 20 seconds to crank through our 40,000 orders. So we got about 11,600 orders per second. That's nothing to sneeze at. I read somewhere recently on Google that Visa processes around about 4,000 transactions per second globally. So if you can get 11,600 transactions per second, that is probably going to be fine for the vast majority of applications you ever build. But we're talking at the extremes here. I will note that if you stay with me and do the hands-on lab after this session, you won't see such high transaction rates if you're going with the always free database, because that's just a single OCPU database. But still, I think you'll be impressed with the numbers. This information here is some diagnostics as to where that time was spent. We burned a lot of CPU and we had a few other interesting things that we're going to tackle now. The first one here, we've got ENQ, CQ contention, and a whole lot of CPU time. Let's have a look at those things now. So the question that comes, if I can get an average turnaround time of 20 seconds and 11,500 transactions per second, can we do better? Triggers that we saw in our quick SQL are just extra code you put in your database, and obviously code consumes CPU. These are the triggers we have, and the reason they're there is to populate surrogate keys, because if the order ID is someone tries to attach null to it, we're going to force it to picking up our next surrogate key using sequence.next file. We had one on the orders table. The problem, the reason we have these triggers is due to this. Historically, if we could put a default on a table, like if the status comes in as null, I want to default it to n. If I don't nominate the status in my insert statement, that'll pick up the default of n just fine. But what this didn't stop was someone explicitly saying, I want to insert a null into the status. That's a problem, because when you did that, even though you had a default set, we would actually get a null in that column and therefore break our database or our data model. So that's where triggers came in to force that value, even if someone tried to put a null in there. But from 12c onwards, we've had more null control. Now, not just default, we can have default on null. So with those columns there, I've got a status, start date, commission, job level, etc. They've all got default on null, which means even if someone explicitly tries to put a null in there, we actually have forced the value of the default in there. With that information, we don't need triggers anymore to populate those nulls. So let's do the next demo now and see what benefit we get from not having those triggers. This will recreate the schema from scratch to make sure we have a common benchmarking baseline to work from. So our customers table, our product table, everything's in there as before. Notice now I've changed the defaults. Default on null to the sequence value. So I don't have to have triggers because default on null will take care of that for me. Order items the same, default on not on null user. All the things that originally I had triggers for are now I'm just using default on null. Constraints, etc. And all the trigger code is now commented out. I no longer need the trigger code in there. The rest of it is the same. Seed the data, create my application, create the benchmark table, create the benchmark. I lock my table in exclusive mode so all the slaves will start at the same time, and we leap straight into it. So once again, all our benchmark slaves absolutely hammering away. Our first benchmark was 11,500 transactions, about 20 seconds of elapsed time. Now that I've removed the triggers, I'm hoping to see some benefits. And here's our result. I've gone from 20 seconds, I shaved off a few seconds, I got down to 18 seconds of elapsed time on average, and I've had a nice little boost in transactions per second. I've gone from 11,500 to about 13,000 transactions per second. That's an excellent result. Most of my time was once again spent using CPU. That's a good thing. We want to use CPU. That's what we pay for. But here's the things we're trying to now eliminate. We've got a thing called ENQ, SQ contention and some buffer busy waits. Let's now see if we can tackle them. ENQ, SQ contention is when we have contention for sequences. Now, caching is a facility of sequences that's meant to handle that. And what happens is people think that caching is going to be an expensive operation. But in reality, sequence caches are not cached. Let me explain. When I do create sequence my sequence, it says we have a default cache size of 20. People think that because we have the word cache in there, that what I've done is allocate 20 pieces of memory in my SGA for all those 20 sequence numbers. Therefore, I wouldn't want to do something like sequence cache 1,000 because that would consume 1,000 pieces of memory. That is not how this caching works. When you create a sequence, we store a thing called the last number. That is the last number that is going to be stored in the dictionary, and the rest of the numbers can be cached up to our cache size. So when I do a select sequence.next val, you'll see that number bumps up to 21. What we're saying is that I can now allocate the sequence numbers 1 through 20 from memory without having to update this data dictionary table. It's that data dictionary that causes the contention. If I have high frequency transactions, orders, order items, etc., there is no memory cost to having a high cache, and it alleviates that dictionary contention. The second thing I want to talk about before we do another demo is what I call the myth of foreign key indexes. Once again, there are numerous blogs out there that say if you don't have an index on every single foreign key column, your database will collapse and die. This is not true. The rule you need to be looking at for an Oracle database between a parent and a child relationship is, do you mess with the primary key? What do I mean by mess by? It means, do you update the primary key? Do you change it? Or do you delete the parent rows? If you do that, you probably need an index on the child table. If having that index on the child table helps performance in its own right, then obviously that's a no-brainer as well. If one of those two things is true, then you need the foreign key index. But if not, you don't. In our data model, if I have customers to orders, am I going to delete a customer and therefore delete all their orders? Probably no way, because financially I'm not allowed to do that. I would probably mark them as deleted, but I wouldn't delete the row because that would remove the order rows from my database. However, if a customer comes in, they're probably going to say, show me my orders, which means it makes sense to have an index on the customer on the orders table. So in this case, this is a foreign key index I would probably keep. If I'm coming in from product to order items, will I ever delete product? Once again, probably not, because it would wipe out all my order history. I'll have a flag that says it's no longer available. Will I come in on the product index for order items? Probably not. I'll probably come in on the order ID. So this is a case where I might not need that foreign key index. So let's run another demo now with a better sequence caching and removing of foreign key indexes we don't actually need. Once again, we'll clear out the entire schema to give us a consistent base for our benchmark. Now you can see the caching I've done on the sequences. Only bumped up the customers 1 to 100, it's not that high frequency, but for our orders, I've gone up to 2000. Why 2000, you might ask? There isn't a hard and fast rule as to what the cache size should be, but since I'm getting around 10,000 transactions per second, a cache of 2000 means I'll be updating the dictionary about 5 times per second. If I continue to see SQ contention, I can just bump up the cache even more. The rest go through as unchanged. I'm keeping this index on the orders table for customer, as we saw in the slides, but I'm not going to keep this index because it's very unlikely I'm going to ever need it for performance or locking perspectives. Of course, this doesn't stop me from doing queries by product. They would just be full table scans. And if I'm doing something like sales per product per year, then a full table scan is probably the best option anyway for scanning large volumes of data. I roll through the rest of the constraints, insert some seed data, there's my benchmark, and off we go. Let's see how we go this time. You remember that without the triggers, we got to about 13,500 transactions per second and about 18 seconds elapsed time. Now, we're making great strides again. I've gone from 18 seconds down to 11 seconds of elapsed time, and now I'm getting 20,700 transactions per second. You can see I've eliminated the ENQ-SQ contention issue. Let's pause for a second here. That's about an 80% improvement on our first benchmark. Often you'll hear of companies spending huge sums of money on hardware upgrades just to get maybe 10 to 20% improvement. And if you flip this around to the world of cloud, then this would mean you could run the same workload for about 80% less CPU, and that directly maps obviously to savings for your business. Now, the two elements that are stopping us from getting closer to our utopia of 100% CPU are buffer busy waits and NQ-TX contention. Buffer busy waits are often contention for table blocks in memory, and ENQ-TX contention is contention for common blocks in an index. Table block contention can manifest itself in many ways, but a first step to treating it is by distributing table blocks more sparsely, and I'll use partitioning for that. Index contention brings us onto the topic of ascending index keys. So let's go back to the slides. Can we do better? Ascending keys. We're using sequences for all of our surrogate keys, and ascending keys can sometimes be a bottleneck when they're being used in indexes. An index is stored as a tree-like structure, and they grow from left to right in terms of ascending sequences. So if every single index key is slightly higher than the previous one, we get contention for that rightmost leaf block. That can be an issue. That can slow down the ability to actually accept transactions. What I can do is hash partition those indexes. And as a result, I'm spreading the index load over multiple physical segments on the disk. The DDL looks something like this. I simply say I'm going to partition it by a hash on the primary key column. In this case, I've nominated 4. That would give me 4 logically distinct indexes, physically different segments on the disk. Therefore, the contention has been spread out over 4 different leaf nodes, and I could make it 8, 16, etc. Let's do our final demo to see if we've managed to improve one more time. Clear out the entire schema. Everything now is kept as before, the caching as before, tables as before. Now you can see in our definitions, I've actually chosen to partition my orders table to spread out the load across the table. I am doing that to alleviate the buffer busy waits, and partition the orders index to spread out the load across those index leaf blocks. I'm trying to scatter workload across the database to improve performance. Same with the order items, and you can see I'm using a slightly different syntax here for the index. The using index local tells the database that the index will be partitioned in the same mechanism as the parent table. So order items and its primary key are both hash partitioned. And now everything else is before, and let's rerun our last benchmark. We're cranking it through. We got to just over 20,000 transactions per second last time at about 11 seconds elapsed time. We're hopefully going to squeeze out a little bit more here. And yet, we just tipped over the 21,000 transactions per second mark at about 11 seconds of elapsed time. Our first demo was about, I think, 11,000 transactions per second, so we've just about doubled it just by making changes to the physical design. But look at that CPU figure. In our benchmark, 99% of the elapsed time is pure CPU. That is ideal for us because we're getting the maximum performance that the underlying hardware can deliver. And it's also a strong indicator that if we needed more performance, then a CPU increase would actually assist. Don't get me wrong, we aim for CPU to be the dominant component when our SQL code is already well-tuned and optimal. If you've got bad SQL, then that can also get a server to 100% CPU, but that is definitely not the aim. In extreme cases, people often even partition their tables across various rack instances to get, once again, bigger jumps in terms of performance. But as we can see here, getting to 21,000 transactions per second is probably going to handle 99.9% of applications in the world today. So at this point, what we've done is go through a number of techniques in terms of physical design to be able to absolutely smash data into our applications as fast as probably they'll ever need. And we've done those demos on a very simple machine, showing that if you move to a more rigorous infrastructure on, say, the cloud, then you're going to get even better levels of performance. So that's fine for ingest, but what about getting data out? It's rare that applications only pump data in and do nothing with that data. So the question is, how can we also speed up our queries to get information out of the database also in a rapid time frame? Let's explore that now, because after all, you're probably thinking, hold on a second, you just dropped a stack of indexes, and indexes are normally the most common technique we use to get query performance benefits. If I'm dropping indexes to get data in faster, aren't I going to have severe consequences when I come to read that data? But one of the aims that we can look for when we're building a physical design is, can we get faster queries, faster performance without altering the indexes we have? We have the same indexes. Can we manipulate the data in some way to get more benefit from those indexes? Let's now do a demo to explore that concept. I'm going to create a table here called customer transactions. It's fictional, obviously, but it's similar to what we'd have in any kind of OLTP system. Namely, we have a transaction ID, a transaction date, effectively a unique ID, and a timestamp as to when some event occurs. In this case, they're customer transactions. And then we have metadata which relates to that transaction, the customer ID, the amount of the transaction, and so on. Normally there's a lot more columns, but these columns will do for the sake of our benchmark. I'm going to populate that data now in a mechanism which looks probably similar to real life. I'm doing it with a single insert, not just row at a time inserts, but the concept is the same. Customers arrive at random times, therefore I'm using DBMS random to come up with a modulo of customer IDs. I've got about 1,000 customer IDs here, but the data comes in timestamp order. Events happen in real time in the real world. So the customers come in at random times and they conduct transactions. Obviously, any customer entering my application is probably going to have an interest in their transactions. So even before I build my code, I'm probably going to have an index on the customer ID alongside the other things like the primary key, etc. What are the typical queries that we would expect customers to do? You'd probably come in and you want to see what my transactions are, etc. So we don't get a lot of data coming back to the screen. This is for ease of benchmarking. I'm going to assume we have an application code requirement, which is a customer may come on and say, what is the largest transaction I've done, in this case, ever? It might be for a time range, but in this case, what's the largest transaction I've ever done? So we can see here that customer 123 comes along and says, what is the largest transaction I've ever done? Luckily, we have an index on customer ID, so this query should be fine. But when I run it, this is what they typically see. This is obviously disconcerting because, like all those studies often show, they say if a customer has to wait longer than, I think it's 3 seconds, 5 seconds, or whatever on a website, then they'll move and take their business elsewhere. I'm not sure if that story is apocryphal or not, but let's assume it is. Whenever customers are seeing this, they're probably going to be frustrated. When I look at the execution plan, I might be thinking, oh, maybe the optimizer chose a full table scan, but it didn't. It did exactly what I was expecting. A query came in with a customer ID predicate, and we used the customer ID index. Everything is as it should be, so why was it taking so long? If we now look at the execution statistics for that query, here is where we start to see the problems. Yes, we used the index, but even with that index, we did a huge amount of physical I/O, which then later translated into consistent gets, i.e. that data was brought into the buffer cache. But that huge upfront cost of physical reads is what has slowed the customer down. If you have an infinitely large machine, then eventually all that information will probably be sitting in the buffer cache and you might be able to get away with it. But generally what happens is data grows faster than the machine infrastructure that holds it. Therefore, eventually, you're going to get to the stage where not all of your data is going to fit in memory. The problem here is not the index, and it's not the data. The problem here is the customers themselves. Customers obviously buy things at a time that suits them. If we draw a timeline here, we can see that different customers come in at different times, obviously when it suits them, to make purchases. I don't do all my shopping on one. That's a bad example, actually. I generally do order my shopping on one day of the year. That's the night before Christmas when I get into a panic. But your normal human being does their shopping when it suits them. And so we can see here that customer 123 might have made some shopping last week and then bought something this week, and they'll do shopping next month, etc. And intermingled amongst their transactions is all the other transactions from other customers as well. That's a problem when it comes to data distribution, because now every time I need to read all the rows for customer 123, what's going to happen is each time I do an index hit, the likelihood of that particular table row being in a different physical block is much higher. Because we have lots of different physical blocks scattered all through the file system or the device, the data file, what's going to happen is the likelihood of each of them being a physical read increases. Therefore, that's where we get those response time issues because we're doing a lot of physical I/O. But there are solutions at hand. In 12.1, we introduced the concept of clustering. Now, I should stress that running that command in 12.1 does nothing to the data. It is simply a dictionary operation saying, I would like data in this table to be sequenced by customer ID whenever that data is bulk loaded or reorganized. So it is purely just a dictionary operation. It doesn't do anything. However, in 12.2, we introduced the ability to move almost any table in an online fashion. What happens now when we combine those two features? The first one says, if I'm doing a major shift of the data or a major load, then sequence the data in order of customer ID. The second operation says we're going to reorganize that data, so during that process, we will reshuffle the data on load to try sequence the data by customer ID. What's happening now is as the rows are reshuffled, and I've got a little pictorial here indicating Oracle blocks, rather than each individual customer's rows being scattered through many blocks, we start to clump the customer ID together into clustered segments. So now the number of blocks of table data which customer 123's data sits in is dramatically lower. Just a quick note here on that previous slide, you can see that the clustering attribute information there, it sits in the documentation alongside zone maps, and zone maps are separately licensed, but this particular feature is not. So as long as you have Enterprise Edition, you can go ahead and use this without worrying about things like zone map or engineered systems, etc. Once I've resorted the data and clustered it by customer ID, let me return to my query. The execution plan hasn't changed. We are still doing our query by index, that is the optimal path in this case. But when we look at the execution statistics, that's where we see the dramatic difference. In my case, I think I had a couple of thousand customer transactions for customer 123 based on the random distribution. All that data has now been clumped into just a smattering of table blocks. Therefore, they'll all very quickly read into memory. I'm still reading the same number of rows, but because it's in a much smaller, much more densely compiled list of physical table blocks, the physical reads drop to a tiny amount. That gives you a huge burst in performance. I want to stress, this is all about choosing the things that are important to you in your application. Now that I've resequenced the data by customer ID, I've obviously unsequenced it, for lack of a better term, in terms of some of the other attributes, for example, timestamp, etc. So what you're looking at doing is finding what matters most to you in your application. In this case, I'm assuming customer ID queries are going to be the dominant factor, the thing that's most important to me, and I'm choosing my physical design to best suit that. You have to come up with perhaps compromise solutions. If you look in the documentation for clustering, there are ways of doing clustering on multiple columns to get a sort of a semi-optimal solution for both columns. You get a slight performance hit on just the one column, but you are able to cluster on multiple columns to get a good compromise solution if those particular columns are the things that drive your application performance. If your response to that is, I'm not on 12.2 yet, and therefore I can't move my table online, which means I would have to take a big outage to take advantage of that clustering, well, I have two things to say there. Number one is, why aren't you on 12.2 or higher? In particular, why aren't you on 19C? 12.1 is going to be out of support soonish. 12.2 I think is already out of support. 11 is long gone. So please, 19C is the version you want to be on and you get access to all this stuff. But if other things have intervened and you're not yet on 12.2 or above, or perhaps you're not on Enterprise Edition, maybe you're on Standard Edition, therefore some of these cool features are not available to you, there are still solutions at hand. One of the things you can look at is DBMS redefinition. That might seem an odd solution because if we look at the marketing line for DBMS redefinition, it was always about changing the actual structure of a table. This is sort of the most common demo we'd see when we look at things like DBMS redefinition. You would start with your typical employee table. That's how it currently stands. And what you want is to somehow dramatically restructure it such that it looks something like this. I've removed some columns, I've adjusted some columns, adjusted some values, etc. I want to do this entire process online. Hence, we want to redefine that table. And we want to do that entire process online. This is where DBMS redefinition was initially pitched. You would create a table with the new template definition that you're planning. You would run DBMS redefinition, a start process, a sync process, and a finish process, and include the column mapping there to map the data over. And you'd go through the process. It effectively creates a materialized view under the covers and a materialized view log to pick up changes. And then finally, when you're all done, you would have your table redefined online with the data moved over as well. I was always a little bit skeptical of that approach because the reality is, yes, I could redefine my table online, but if I've changed all the columns and changed all the data, well, there's probably a few other places in my enterprise that I'm going to have to dramatically rejig the code as well. You can't just change the underlying database structure without having to change all the things that depend on it. All your code, all your views, all your Pure SQL programs, your forms programs, your data analysis queries. There's a lot of stuff that needs to go on. And I think that's why DBMS redefinition for that purpose probably never really took off. One little known use for DBMS redefinition, which I think is very cool, is you can redefine the table to a new table with the exact same structure. Now that seems a bit of a contradiction in terms of why would I want to redefine it and yet leave it exactly the same as before? It all comes down to this critical parameter in DBMS redefinition, which is the order by clause. While we are redefining your table to its identical counterpart, we will sort the data. This is equivalent to doing the clustering effect. So if I sort by, for example, customer ID, even though I'm changing a table from one structure to an identical structure and moving all the data across, while I'm doing so, the initial load of data will be done with a sorting clause. That lets me achieve the same clustering result that I saw with the 12.2 and above facilities, and I can do it in earlier versions and in standard edition. It's a little bit more manual work, but still you have that benefit of dramatically improving certain index access paths by resequencing the data. Can we take it one step further? Can we get faster queries even if we have no indexes on the data? What can we do if there is nothing except just the data itself? One thing you might want to consider is the use of partitioning as an indexing strategy. We often think of partitioning as just, this is how we're going to archive our old data, etc. But if you think about in this sort of general approach of when you're trying to performance tune a query, what are we actually trying to optimize here? The query performance or the query efficiency really comes down to a simple ratio. How much data do I need to scan and how much data do I actually get? If I can keep those things very close, then I've got a very efficient query. If I have to scan 1,000,000 rows to get 10, it's inefficient. If I have to scan 20 rows to get 10, then the query is nice and efficient. It's that ratio that I'm always trying to keep down to 1-to-1 that gives me the most efficient queries possible. Where partitioning might come involved in that is the concept of partition pruning, the ability for the optimizer to eliminate partitions from consideration where possible in order to minimize the amount of data that has to be scanned. If I can eliminate partitions from being scanned, I'm going to improve the efficiency of my queries by limiting it to just the rows of interest. Here's an example of partition pruning in place where, assuming this table is partitioned by the timestamp column, being able to put in a particular date, the execution plan tells me I didn't scan the whole table, even though it says table access full. It says partition range single. I only scanned a single partition as opposed to all partitions for the table. So to use partitioning as an indexing strategy, what we could go for is very granular partitions, such that partition elimination mimics the effect of using indexes to eliminate vast majority of the data from consideration. I like to call it hyper partitioning, just because it's a cool name. I just made it up. You won't see it in the documentation anywhere, but let's call it hyper partitioning for the sake of the rest of this session. Now, I want to stress, hyper partitioning only really becomes an option for you though, as long as you're on 18C or above, because two key features came along in 18C. Remember I said you should be on 19C or higher? Here's another justification. There are two features in 18C when it comes to merge partition that are critical if you're going to go for a very granular partitioning strategy. The first one of these is the ability to have more than one partition now in a merge command. It used to be the case that if you wanted to merge partitions, you have to nominate two of them to become one. If you want to merge 10 partitions, you would have to go through them in pairs at a time. It was a long-winded process. Now in 18C and above, there is no limit. You can simply list as many partitions as you want to merge into a single partition. And the demo on screen there starts to allude as to the kind of things you might want to consider. In this case, I've got daily partitions, and I'm going to merge all 31 partitions into a monthly partition. The second thing that's critical from 18C onwards is the ability to do that merge operation online. It used to be the case that merging, splitting, and most of these partition operations would involve effectively taking the application away from customers because you were doing a heavy-duty, resource-intensive operation, which might take some time, and the whole table is locked while that is going on. Now that you can merge partitions online means you can do these maintenance operations without an interruption to service. You simply add the online keyword to your merge operation. We recommend you do these online operations in quiet periods. Don't get me wrong, there is an impact to doing it online. You can see one of my videos on my YouTube channel, which talks about the fact that it also uses slightly more space. But the fact that you can do it online in a quiet time opens up opportunities for you to do partition maintenance without taking the application away from your customers. How does that help queries, you might be asking? This section was all about faster queries with no indexes. Let's build up an example now to demonstrate where that might be useful. I'm going to create a table called sales. I'm going to partition it at a very granular interval, literally by the hour. So even just for today, I'm going to have 24 partitions for every single hour of data coming in. The reason I want to do that will be evident shortly. When customers say, show me the sales just for the last hour or the last few hours, the execution plan reveals the benefit of having that hyper-partitioning strategy. For just the last hour, you can see I eliminate almost all of the table's partitions. I'm simply getting the partitions for this hour and perhaps the last hour. Effectively, what I've got now is just 2 hours worth of data that I need to scan. That's going to be very, very efficient compared to scanning even a week's worth of data. By having these very granular partitions, I'm effectively mimicking the benefit of indexes here. If I fast forward a day, then of course now I'm starting to accumulate a large number of partitions. After a day or so, I've got, in this case, about 40 partitions. I've got some for today and all of yesterday's partitions. When it comes to looking for yesterday's figures, yes, I'm going to have to scan now 24 partitions, but still, I'm only scanning the data that applies to the query range. Remember I said query efficiency is the amount of data you have to scan versus the amount of data you want to get back. If I'm looking for a day's worth of figures, I'm just scanning exactly that 1 day's worth of figures. I'd actually argue this is probably even better than having indexes because the moment you get into large volumes of data, let's say there's 1 million rows for yesterday, then index access to 1 million rows can be very, very expensive. In this case, we're doing the benefits of multi-block reads, but still just for the data that we require. But there's no such thing as a free lunch. If we go into fast forward, say, a year later, well, now I've got a lot of partitions. 9,000 partitions isn't a big drama to the Oracle database in the sense of number of partitions, because we can accommodate, I think, 1 million partitions in a table. But if we start looking at the metadata that surrounds that, each of those partitions is effectively like a table in its own right. So it's going to have information for the optimizer on those partitions. So we've got effectively, in this case, 10,000 or so histograms. When we go look at the histogram distributions, we're now getting into very large amounts of dictionary data. When I start throwing complicated queries against this table, that's a lot of information that the optimizer has to drag in from the dictionary case, go through it, go through all the calculations, and try work out the best way to run a query. Once you start getting into tens of thousands of partitions, the parse time for queries can go up simply because of the volume of data the optimizer is churning through to work out how to best run your query. But the solution is from 18C onwards, rather than letting those partition numbers just grow without bound, we can merge those partitions in an online fashion, and we can do it very selectively based on the user requirements and the application requirements. I've got a little bit of PL SQL here, which will simply loop through some partitions. In this case, I'm just using, I think, the partition name to come up with a DDL merging strategy. I run that and it spits out the following DDL. It's going to merge all my hourly partitions into a day. And then you simply choose the merging strategy that's going to work best for you. If you have real-time hourly trend analysis that needs to be done, you would go for hourly partitions. Similarly, for a daily summary, hourly is going to be fine. If you start having information about the current week, then you probably want to look at merging those hourly partitions into daily partitions on a regular basis. Even month to date is probably fine with daily partitions. You'd be looking at a maximum of 30 partitions to scan. But then as the volume of data grows and the partitions grow, and you're looking at doing things like yearly trends or 10-yearly trends, you may choose to then merge those daily partitions into weekly, monthly, whatever suits your needs. If your application doesn't do some of these things, you could get away with, for example, going from, say, hourly to monthly or hourly to weekly. You can choose, mix and match the partitioning merge strategy that's going to work best for you. Let's now wrap up this talk about, hopefully you've now seen that physical design is critical. It's going to help you with getting data in exceptionally quickly, more than what you'll ever need for most application requirements. It's also going to help you get data out very, very efficiently. None of these things did we actually change the code in our applications. We simply manipulated the underlying database design to suit the best needs of our application requirements. And hopefully you agree that none of this was breathtakingly complicated. We didn't use any specialist features or niche parts of the Oracle database. We simply use the things that are covered in the fundamentals: how to best lay out your data, how to best organize your index structures, and how to take advantage of partitioning to make sure that we have that good ratio of query data efficiency versus data you need to scan. And all of this is straight out of the Oracle documentation. Whereas most of the documentation is reference material, a couple of good guides I would recommend would be the concepts guide, because it's laid out differently. It's not really a reference, it's more of a description of how the Oracle architecture works, and that's the key sort of background fundamentals that's going to help you come up with good physical design decisions. Also, the application developers guide takes those concepts and puts them more targeted at a development process. So if you're a developer watching this, the application development guide goes through all those particular fundamentals to come up with the best way of laying out your tables without too much underlying knowledge of the Oracle internals. If you can do those two things, I guarantee you're going to know more about good application performance and database design than the vast majority of current people out there, no matter what their level of experience. Because without those fundamentals, people have spent careers making the wrong decisions when it comes to Oracle database design. But I want to stress, as we saw earlier, if I just build something in QuickSQL, it might not be the 100% optimal physical database design, but as we saw in our first benchmark, I think we were still getting about 10,000 transactions per second. It's going to be perfectly adequate for the vast majority of applications out there. Just fire up your QuickSQL session, get yourself a starting point for your database design. It's going to be very, very robust and probably good enough for most of your applications. But if you have a stunningly successful application, knowing how to get from good up to great, fantastic database design to get those incredibly insane performance numbers is a very useful skill to have. Thanks very much for watching. I hope you enjoyed this session. And if you want to get in touch with me, once again, reach out to me on Twitter, or you can catch me up on my blog, or reach out to me through my YouTube channel. Just to be hip and trendy, I've got the QR code there. If you click on that, it'll take you to Linktree, which has all the ways you can get in touch with me, including podcast, Instagram, Facebook, you name it. I love talking technology, so please reach out to me, follow me on Twitter, and we can continue making our applications successful with the Oracle database. Bye for now.
CloudDB, shaping your new normal.